I'm so sorry, everyone. There was some problem with the connection. Can you all can you all hear my voice now? Okay. Okay. Thank you. Right. Fine. So voice is clear. Now, I hope you can see the screen as well, right? So we were talking about why is the value of dV zero. The answer is that the change in potential will be zero, right? Because we are moving on an equipotential surface, right? So if you take 2 points on equipotential surface, then the change in potential is of course zero. All right. So that's why dV is zero. Now because dV is zero, because dV is zero, I can say that E minus E dr cos theta is zero, right? Okay, I've just put dV's value that we have over here, right? So minus E dr cos theta is zero. Now we have not specified in which direction we are moving, right? That is, this will happen even if dr vector is in any direction, correct? This will happen if dr vector is in any direction. All right. Okay, so that means this whole answer that this is equal to zero is irrespective of how you are moving on the equipotential surface, right? So this will ultimately only be possible for all cases if cos theta is equal to zero, right? That is, E vector and dr vector may be in any direction, right? But still they may have any magnitude, but the angle between them will be 90, right? But right, because cos theta is 0, so theta is 90, right? And but we are moving on an equipotential surface, right? And this is a small displacement, right? I'll repeat what I've said. We are moving from some point A to some point B, so this is dr vector small displacement, right? And it is on an equipotential surface. So this actually means the equipotential surface is this means equipotential surface must be at 90 degree to the electric field vector, right? Only then every time you can get the angle 90, right? Okay, so let's see this, what happens in this example, right, of a point charge. So these are the spheres which are equipotential surfaces, right? Because here at every point on this surface A, B, C, D, everywhere, the distance is r, right? Okay, so the potential is same. So what I mean to say is, if you consider such equipotential surfaces for a point charge, right, then I hope you all still remember that for a point charge, the electric field is always in the radial direction, coming out like this, right? Okay, for a positive charge, the electric field vector will come out like this from every point. So at every point, right, green is the equipotential surface. At every point, because it's a sphere, the radius is always perpendicular to this surface, right? That's what we already know. We talked about it in the first chapter. So that's why we are getting that electric field, which is in direction of radius, is always normal to this equipotential surface, right? It is always normal to this equipotential surface, right? And that is always going to happen because of this little calculation, right, that we are seeing. It explains why equipotential surface should always be at 90 degree, right, with the electric field. All right. Okay. So now based on this, you can actually talk about direction of electric field. You can say that direction of electric field at each point is normal to equipotential surface, right? This is an important sentence. It tells you about direction of electric field. All right. So now, okay, we have talked about direction, right? Let's go back to this formula and continue about that a bit more, right? Then we'll go to magnitude. So I'm writing the formula that we had again, okay, right? So this means if you want to find the direction of electric field, then dr, if it is such, listen to this carefully, if you want to find direction of electric field, then the dr vector, right, if it is in the same direction as electric field, all right, if electric field vector and dr vector are in the same direction, then theta is 0. If E and dr are in same direction, then theta is 0, right? Now if theta is 0, do you realize that dv, which is equal to minus E dr cos theta, right? Then dv is going to be maximum in value, right? In value, that is in magnitude, right? But I don't really like to put magnitude. I just put modulus here. So then this would mean modulus dv is maximum in value. Why maximum? Because if I put theta is 0, I'll get cos theta as 1, right? Okay, so if cos theta is 1, then modulus dv is maximum in value, and that would mean that decrease in potential. Okay, see what is meaning of decrease in potential? Decrease means opposite of change, right? Change is always final minus initial, correct? And decrease means initial minus final, right? That's called decrease. So decrease in potential is actually minus dv. I'm sure you all understand that, because dv is change, so minus dv is decrease in potential. So this is going to be E dr cos theta. Just put the minus sign on that side. And this will be maximum because cos theta is 1, right? So finally, to sum it up, I'm saying that if displacement is in direction of electric field, if dr vector is in direction of electric field, then decrease in potential is maximum, right? Okay, if displacement is in direction of electric field, the decrease in potential is maximum. That means if you want to find out in which direction is electric field, suppose if you want to get one more way to find out about direction of electric field, then we can write this sentence: electric field is in the direction in which the potential decreases maximum, right? Have you understood this sentence? See, this is actually a very tricky thing, okay? If you have questions, please ask, don't hesitate. There are so many concepts going on over here, right? So let's revise what we have studied in this topic. So far, it's not over, I know. So far, I've said that first of all, equipotential surfaces are surfaces which have equal potential at all points, right? Okay, so we took an example. We said that if there is a point charge like this, then the equipotential surface is a sphere, right? It's spherical because the potential only depends on distance r. So you take same distance everywhere. So you get equipotential surface because A, B, C, D, E have same potential. Then we talked about what's the relation between electric field direction and equipotential surface. As you can see, so I said that in general, if you write dv is minus E vector dot dr for small displacement, then to get dv equal to 0, you're going to have to put E vector and dr vector perpendicular to each other. That is, the angle between them has to be 90, right? So that says that means equipotential surface is at 90 degree to the electric field, right? So we took, so it means at any point, if you want to draw equipotential surface, then you draw it perpendicular to electric field, or vice versa. If you want to draw electric field, then you draw it perpendicular to equipotential surface. So this is an example. If green line is the equipotential surface, right? Okay, then it's like a sphere. So electric field is coming out radially. That's what we studied in first chapter. So you can see at every point, the angle between these two is going to be 90, right? That's what we have understood so far. So then that brings us to this final sentence. That direction of electric field at each point is normal to the equipotential surface, right? Normal, that is perpendicular, all right? And then we talked about another way. To find direction of electric field. It says that if you write dV is minus EDR cos theta, then the decrease in potential is EDR cos theta, right? And if you want to make that maximum, you should put cos theta as 1 or you should put theta as 0, right? That is E vector, and dr vector. E vector, dr vector must be in same direction, right? So that brings us to this final sentence, that if you want decrease in potential to be maximum, then displacement should be in the same direction of electric field. It means if you go in direction of electric field, then the potential decrease is maximum, right? Okay. Now your question, sir, Swarali. If there are two charges on equipotential surface, it doesn't matter, right? Here we are talking about source charge, right? Suppose this is a point charge which is the source of this electric field, and then we are putting test charges to check how much is the potential. So these Q, they are test charges, and generally we consider that test charges are small, okay, and they don't matter, right? They will not change the electric field of this source charge, right? So it doesn't matter, right? But if there is something like dipole, then we can talk about that actually, right? But let me finish the theory, then we'll talk about dipole's equipotential surface, all right? First, let's complete the theory. Okay, so far we have been talking about direction only, right? We have been talking about direction of the electric field. I told you two ways. One, perpendicular to equipotential surface, and second is in direction in which potential decreases maximum, right? Now we talk about magnitude. Yes, Hodel, this sentence, right? This sentence here and this sentence here, they're always true, right? Because we have not derived this for uniform field. They are true for anything, right? Okay, we don't even know what is electric field like. They're always true. Okay. So now I'm going to talk about magnitude. Let's talk about magnitude of electric field. See, we go back to the same formula. dV is equal to minus E dr cos theta, right? if you want to talk about magnitude of electric field, then do you realize it is going to be like this, right? I don't think anyone has any problem with that, right? So now I can say that the magnitude of electric field, if you want to find the magnitude of electric field, then okay, let me just draw a diagram. I think that will make it easy for you. Suppose this is direction of electric field. All right. So do you realize that equipotential surface will be normal to this? So this is equipotential surface, EPS, short form. Okay, EPS, equipotential surface, right? So that it is perpendicular to it, right? Then let's say displacement vector is in this direction. Suppose we move from this point A to another point B in space. So this is dr vector, right? Then this is theta, angle between E vector and dr vector. All right. Okay. So now, if we want to define this or write it in words, I'm sorry, there was a phone call, so I got a bit distracted. Let's continue. If you want to find the magnitude of this electric field, then you can say it in words as follows. It is the ratio of, or you could say, sorry, the change in, actually decrease in, the decrease in potential per the decrease in potential per unit, decrease in potential per unit displacement perpendicular or normal, to equipotential, let me write EPS, okay, equipotential surface. How did I make this sentence? Let's read this. Okay, decrease in potential. What is meaning of decrease in potential? This. All right, minus dV is decrease in potential. We talked about it earlier, right? Okay. Then what is dr cos theta? Dr cos theta. Look at this diagram. We have dr vector. Let's take its components. Okay. So one component is going to be like this, and another component is going to be like this. So do you realize that this green component, which is in direction of electric field, is dr cos theta, right? I hope you understand what I'm saying. This is dr vector, this is theta angle, then this component should be dr cos theta, right? Okay. So read this now. So this is decrease in potential, that is minus dV, right? Per means divided by dr cos theta. Dr cos theta means, what is meaning of dr cos theta? Component of displacement perpendicular to equipotential surface, right? Because this is the direction normal or perpendicular to equipotential surface, right? Okay. So this thing, this whole sentence is giving you, right, this decrease in potential per unit displacement perpendicular to equipotential surface, this is equal to magnitude of electric field. Say yes or no. Have you understood? સુઈ ગયા ને આજ તો આજ ખતરનાક ભણાયું ને. The topic today is very abstract, or it's like imaginary things. think about equipotential surface, right? આખો concept જ imaginary છે ને. We are alive. Okay. Explain last sentence. Okay, fine. I am doing it again. I understand that it's a bit tough. Okay. Sir, we survived. Can cuboid be considered as equipotential surface? Okay, Darshi, I'll answer your question very shortly. Let me first explain this sentence again. Okay, so again, going back to this relation, let's watch this carefully. Numerator. What is the numerator? Minus dV. Minus dV means decrease in potential, correct? Okay. And then that we are dividing by, let me draw one more diagram here. Suppose this is electric field at this point, then the equipotential surface is perpendicular to that electric field, okay, like this, right? And now suppose I draw a dr vector in this direction, okay, and this angle is theta, right? So what is meaning of dr cos theta? Look at this diagram. This dr, if I take its component like this, then this component is dr cos theta. Use trigonometry, correct? Okay. So decrease in potential, that is this, per means divided by what? Displacement perpendicular to equipotential surface, that is dr cos theta, right? Again, decrease in potential means minus dV, that divided by dr cos theta, which is displacement perpendicular to equipotential surface, right? Then that division gives you magnitude of electric field, right? Okay, I hope it is better now. Aman, if you have not understood everything, you could ask, no problem with that. See, remember all this, all the discussion that we are talking about, right? You should get it that it's like we are thinking of moving a test charge, that's it, right? All of this is going on in our mind, right? Okay, if you want to do an experiment, you'll have to do it like this. That's what we are thinking, right? Okay, and then we, let's say, measure the potential here at A, and then we measure it at B, right? And then we find the small decrease in potential, that's this, and then we divide by dr cos theta, or how much we have displaced this, and then take perpendicular component, right? So based on that, we will get the value of electric field. But right now we are just doing it in our mind, right? That we will move a test charge and this will happen and that will happen, like that. Okay. Obviously, you cannot do it practically very easily because single charge is very small, isn't it? Right? You cannot hold an electron and make it move. Okay, go there. That's not going to happen, right? But this is how you can think about it, right? Okay. So this is magnitude, right? Now I want all of you to read these sentences that I've explained, right? These sentences are given in your textbook. They're given on page number, they're given on page number 61. Okay. नेट केम बंद થઈ જાય ને બેટા પાવર સપ્લાય બંધ કરે માંડ સમજાય તો આ બંધ નથી એટલે કે તારે આટલું એમ નહીં શું બંધ નથી જો મેં